Theoretical computer science operates on a very convenient assumption that algorithms have access to absolutely limitless computational power. Out in the real world, an AI system is strictly bound by the inflexible physics of its hardware. It only possesses the processing power and memory physically wired into the silicon. Capping the compute time of a processor forces the system to make decisions before it actually evaluates the full picture. Bounding the memory capacity and power draw creates a massive physical bottleneck, especially for small edge devices trying to run modern algorithms. Deploying real-world AI requires translating pure math into engineered intelligence that can survive hard physical boundaries. The engineers working on early AI search engines faced a rigid temporal limit. Their systems would quite literally run out of time to calculate the next move. To keep classical evaluation functions like minimax physically feasible, programmers had to mathematically cap the search depth. Decades later, modern deep learning faces a spatial limit. Massive deep neural networks run out of memory. Engineers cannot rely on brute force scaling to put these models into edge computing devices. They have to structuralize immense mathematical complexity into finite boundaries. Whether calculating a chess game or powering a smart camera, it relies on strict structural mitigations to survive its hardware limits. Classical AI mapping explores future consequences by branching every possible move into an expansive game tree. Because every turn multiplies the possibilities, evaluating a full game tree down to its absolute end state is computationally impossible. The branching is exponential. To cope with this, evaluation algorithms utilize techniques like alpha-beta pruning to drastically limit the scope. This establishes a search depth, a fixed mathematical limit on the exact number of turns the machine is permitted to look ahead. While mathematically necessary to keep the system running, evaluating a partial tree yields highly misleading strategic results to the algorithm. In 1973, Hans Berliner named this vulnerability. He called it the horizon effect. Imposing a rigid temporal boundary artificially blinds the AI to disastrous, unavoidable consequences sitting just beyond its search horizon. Consider a chess scenario where an AI's compute limit restricts its evaluation function to a strict search depth of 6 plies. Based on the board, the evaluation function correctly calculates that its queen is lost exactly at the 6th turn. But the algorithm discovers an alternative path. Sacrificing a rook at the 5th ply dynamically shifts the timeline. This diversionary sacrifice mathematically pushes the loss of the queen down to the 8th ply. According to the algorithm's naive scoring logic, losing a rook at ply 5 objectively scores better than losing a queen at ply 6. The system chooses the diversion. It delays the inevitable while actively worsening its position by eventually losing both pieces. The negative horizon effect forces the machine to create ineffective diversions, mistaking a delayed failure for a strategic victory. Engineers mitigate this blind spot using an algorithmic sex called quiescence search. The mechanism reallocates processor time away from stable, mathematically quiet board states. The saved compute is then dynamically spent extending the search depth specifically for volatile nodes, breaking the rigid boundary. If there is a pending piece capture, the search is forced to continue until that chaotic exchange is fully resolved before scoring the position. This asymmetric resource allocation prevents the machine from blindly evaluating a volatile moment, neutralizing the illusions created by a flat horizon. While early AI struggled with classical temporal limits, modern deep learning is governed by strict spatial limits. In modern machine learning, engineers realized that accuracy scales exponentially with layer depth. This chart shows the ImageNet challenge results from 2010 to 2015. The data proves that state-of-the-art performance requires moving from shallow 8-layer networks like AlexNet to massively deep architectures like the 152-layer ResNet. A 152-layer architecture requires a massive memory footprint that cannot physically run on a constrained edge computing device. Highly accurate theoretical models hit a spatial wall, rendering them entirely undeployable without radical structural compression. Engineers utilize model compression to bypass the edge memory bottleneck, shrinking the network's footprint without a catastrophic loss in accuracy. The first technique is pruning. It systematically removes the redundant nodes and weights that contribute the least to the AI's output. This trades a negligible drop in accuracy for a drastic reduction in the physical memory size required by the model. The second technique, quantization, attacks the precision of the network's internal data rather than its structure. Quantization algorithms lower the bit precision of the AI's weights, dropping them from complex 32-bit floating points to simple 8-bit integers. This mathematical rounding process exponentially reduces the required memory bandwidth for the device's chip. Pruning and quantization structurally lighten the load, forcing massive algorithms to survive inside tiny silicon limits. Knowledge distillation offers another path, transferring intelligence rather than just deleting weights. Engineers utilize a massive, fully trained teacher network to guide the training of a miniaturized, deployment-ready student network. Finally, engineers deploy a highly structural mathematical technique, low-rank factorization. This involves taking a massive weight matrix containing a high computational load and splitting it. Factorizing a large matrix with rank R into two smaller matrices drastically reduces the physical operations the processor must actually compute. Distillation and factorization prove a crucial point. An AI's intelligence is not inherently dependent on its raw, uncompressed spatial mass. Whether evaluating the chronological depth of a game tree or the spatial depth of a deep network, naive scaling always fails. Theoretical algorithms must be reshaped to fit exactly within the physical limits of their operating environment. Hardware capabilities will never infinitely scale to match the theoretical bounds of computer science algorithms. Pushing past a computational horizon requires discarding symmetry in favor of asymmetric resource allocation and structural compression. True progress in AI engineering relies on an algorithm's efficiency, not just its theoretical accuracy. Real-world AI ignores theoretical perfection on an unlimited supercomputer. It demands engineering intelligence to survive the strict physical limits of reality.